If you take a solid block of metal and expose it to a shifting magnetic field, something invisible wakes up inside the material. Whenever a bulk conductive material experiences a change in magnetic flux, the metal reacts by generating localized electrical currents right inside its own volume. Because these internal currents form continuous, swirling loops that resemble whirlpools in a river, physicists call them eddy currents. The mechanics of this reaction are dictated by Faraday's law of induction. The faster that magnetic flux changes, whether the field is moving or the metal itself is moving, the stronger the resulting current will be. But this creates a massive engineering challenge. Because these continuous internal currents flow against the metal's own electrical resistance, they rapidly convert kinetic and electrical energy directly into heat. Controlling this force relies on the deliberate manipulation of the conductor's physical geometry. Understanding how to manipulate the metal's shape to either harness or suppress these eddy currents is a strict prerequisite for designing modern transit braking systems and protecting global electrical grids from thermal failure. To see exactly how these currents form, we can look at a classic kinetic model. This diagram illustrates a copper plate swinging into a magnetic flux region of blue X's. Notice the reaction. The eddy currents, the red looped arrows, don't form across the whole plate. They localize strictly at the entering and exiting boundaries. Isolating this interaction in a 2D cross-section makes the internal forces clearer. Swirling loops of electrical energy only materialize at the interface line. Metal crossing the boundary experiences a massive flux change, while the interior, where the field is constant, remains inert. What happens next is governed by Lenz's law. An induced current always flows in a direction opposing the change that created it. These new electrical loops instantly generate secondary magnetic fields that project outward, actively pushing back against the original rigid flux lines. This magnetic interaction forces the plate to do mechanical work, converting its forward kinetic motion into an opposing electromagnetic drag that rapidly damps the pendulum. We can test the strength of this electromagnetic drag force by pitting it directly against gravity. This note sheet documents an experiment, comparing a magnet dropped through aluminum versus PVC pipes. The non-conductive PVC provides our baseline. The magnet falls at standard gravity. But in the aluminum pipe, a physical anomaly occurs. The magnet takes significantly longer to emerge. Aluminum isn't magnetic, so the pipe isn't attracting the metal. Instead, as the magnet falls, its flux lines continuously sweep through the conductive walls. The solid pipe acts like a continuous stack of individual conducting rings. As the magnet drops, each sequential ring experiences a rapid change in magnetic flux. Directly below it, large eddy currents form in the pipe wall, creating a magnetic pole that repels the falling magnet, pushing upward. Simultaneously, in the pipe wall directly above the magnet, retreating flux lines generate a different set of eddy currents. These create an attractive magnetic pole that pulls upward on the magnet as it tries to drop away. This dual macroscopic damping, pushing from below and pulling from above, forces the magnet into a terminal velocity far below 9.8 meters per second squared, defying standard gravitational expectations without ever physically touching the pipe. Moving past laboratory experiments, engineers scale up this physical phenomenon to harness extreme drag and generate massive thermal energy in heavy industry. The exact macroscopic damping force that slows the falling magnet is identical to the mechanism used to slow mass transit. Placing powerful electromagnets near the solid, spinning metal wheels of a train induces massive eddy currents on demand, providing extreme deceleration through non-contact induction. But thermodynamics demands a trade. The immense kinetic energy erased during that braking process must be converted into another form. As the swirling eddy currents force their way through the bulk metal of the wheel, the metal's internal electrical resistance converts all of that electrical energy directly into heat, safely burning off the train's momentum. This exact process of generating heat via resistance is intentionally weaponized in heavy manufacturing. Inside an induction furnace, large volumes of solid metal are bombarded with rapidly alternating magnetic fields. The resulting eddy currents are so intense that the electrical resistance melts the metal entirely from the inside out. This principle works for precision applications too.
Controlled eddy currents regulate the spinning metallic disc inside an analog power meter to track household electricity usage. When the conductive bulk volume is large and unrestricted, eddy currents are powerful enough to safely halt a commuter train or melt industrial steel. However, that exact thermal conversion becomes a critical vulnerability when it threatens the core infrastructure of the electrical grid. As these notes indicate, in AC electrical systems, eddy currents are highly undesirable because they continuously dissipate valuable electrical energy in the form of heat. Transformers are uniquely vulnerable to this. They rely on massive bulk iron cores that are subjected to continuous alternating currents, meaning the magnetic flux inside the metal is changing rapidly and constantly. Unmitigated, that changing flux induces massive, unrestricted eddy currents inside the bulk core. The resulting heat quickly triggers thermal runaway, compromising the core's structural integrity. To stop this, engineers utilize a specific mitigation strategy, physically breaking up the metal into laminations, separated by thin layers of an insulator, like lacquer. Instead of using one solid block of iron, the core is manufactured by slicing the geometry into dozens of thin vertical sheets. Between every single sheet sits a microscopic wall of insulation. These physical boundaries fracture the internal electrical flow. When the magnetic field shifts, it can no longer generate one massive swirling current. Instead, it forms hundreds of tiny, disjointed microloops, permanently trapped within their individual layers. Restricting the physical radius of these loops drastically increases the electrical resistance they face. This forces the current magnitude to drop, preventing massive heat buildup. Lamination is an elegant geometric hack. It allows the metal block to safely carry the vital magnetic flux it needs for grid power, while mechanically strangling the parasitic currents that would otherwise damage the system. The rules established by Faraday and Lenz regarding electromagnetic induction are absolute. Eddy currents are an inescapable physical reality for any bulk conductor placed in a changing magnetic field, but their impact changes entirely based on how we engineer the material. Whether this force acts as a powerful tool or a parasitic enemy depends entirely on the conductive volume of the metal itself. When engineers demand kinetic damping to stop a train or raw thermal output to melt steel, they maximize the geometry into thick, solid blocks to let the currents run wild. And when they demand pure electrical efficiency, they systematically slice and fracture that geometry to choke the currents out. Mastering electromagnetism involves architecting the physical shape of the metal to dictate the behavior of the invisible, swirling currents dancing within it.